Good evening, everyone. Uh, Let us wait for 2 to 3 more minutes and see if somebody else is joining. We can start the session then. Let us just wait for another minute before beginning the session. Okay, so let us begin today's session. I hope that the screen is visible to everybody and that I am audible to everybody.
Yes, sir.
Okay,
Yes, sir, you are audible.
Yes, sir.
thanks. So, okay, so I welcome all of you to the first live session of the course Fundamentals of Manufacturing Processes, which is being offered by Dr. Professor D.K. Dwivedi of IIT Roorkee. As in for myself, I am a Big Dev PMRF PhD scholar in the Department of Mechanical Engineering at IC Bangalore, and I shall be helping you with the problem solving sessions in this live interaction classes, wherein we will be solving some of the problems related to the concepts that were discussed in the previous week theory class of the course, just to help you or to give you an idea about how to go about the assignment problems. At any point of time, if there is any doubt in any of the concepts, please do interrupt and ask. uh, please do interrupt and ask so that we can clear the doubts right then. And if there is any doubt pertaining to the theory classes, I encourage all of you to use the discussion forum of the NPTEL course, so that both the professor as well as the TAs can solve the doubts pertaining to the theory classes there itself. So, without any further delay, let us begin today's session. So, today we shall be discussing a few problems related to the basics, the very basics of the manufacturing process, their classification, and on what agenda they have been classified, on what aspects they have been classified. So, it is just a very preliminary session and very introductory concepts of to manufacturing processes. I am quite certain that most of you are already familiar to with all of these. So, but let us just begin it with this introductory session, so that in the previous weeks, when more complicated concepts are being discussed, we can go about them easily. So, let us begin. And Most of the problems that we'll be discussing today will be theoretical problems, because uh, uh, just these are introduction. This is just an introduction to the manufacturing process, and with time, if and when there is some formula or some numerical problem being discussed in the theory class as well, we will try to solve those as well. Okay, so I hope that all of you will be benefiting from this course, and I request all of you to attend these live sessions every Tuesday from 6 to 8 p.m. and make this outreach a success. uh, okay, so the first problem that we'll be discussing is it is related to like a classification of the manufacturing process. So a mild steel rod, it is a mild steel rod from 50 millimeters to 40 millimeter diameter as a finished product can be classified as what? As a positive process, as a zero process, as a value removal process, or a value addition process. So before we go into what kind of process it is, let us first discuss what are the processes, what are this positive, zero, and the value removal process and value addition process. Okay, so um,
The option C is correct.
the option.
Option C is correct.
Okay, so any other answers?
Yes, sir. Option C is correct. Value
Sir,
removal
option C is
process.
correct.
Okay, okay, so let us first try to understand what these processes are. The so what is this positive process? So a positive process is
The
something.
joining processes like welding.
Yeah,
Welding, sir. Welding.
joining processes like welding. What happens in that?
Just shouldering.
Sorry. So how will you classify that it is a positive process? Joining is a kind of process. So what is the basic principle of a positive process?
Sir, we are adding some material.
Yeah. So basically, the mass is will be added. So mass is added. Okay. What is a zero process?
Sir, casting.
Casting, farming.
Sir, casting and forging.
No addition, no
Zero process.
removal.
Yeah. So it is basically a mass conservation process. Like casting and forging.
Forging. Forging.
It's basically forming. So any kind of forming processes, including forging or extrusion or anything. And what is this? Now, what is this value removal? or sorry.
Machining.
Okay.
Machining process is the value removal processing.
Okay, so before we go into it, so there is a different classification. What is a negative process? So what is the difference between this value removal process and a negative process then?
You have to write value addition in place of value subtraction.
No, then I am asking what will be the difference between a negative process and a value uh, removal process or a value subtraction process.
One and the same, sir.
Okay, so I would like to mention here that it is not exactly the same. Uh, Actually, it is quite different. So, a negative process is one where the mass is being rejected from the original system, like machining. And value removal or value addition process comes in a different, totally a different aspect, like if the final product is having a greater use or greater quality as compared to the initial product before processing, then that will be a value addition, that we are adding the value to the original product. And if the final product is having a value or less usefulness to the user than the pre-processed product, then it will be a removal of the value. It is not a mass removal process or a mass addition process, it is a value. So you have to focus on the word value. So when we are turning a mild steel component from 50 to 40 millimeter diameter as essentially a finished product here, so finishing the product, it will have a higher surface finish and it will be more dimensionally accurate. So in that we are adding value so that it is more useful to the end user. That is why it is not, the value is not getting removed from the substrate or the pre-processed component. Rather, the value is being added in this process so that this finished product is having a higher value than its pre-processed counterpart. So now is it clear what is the difference between this value removal, value addition and this negative process?
सर एग्जांपल दे दीजिए नेगेटिव प्रोसेस का और वैल्यू रिमूवल प्रोसेस का.
ओके, सो जैसे कि यू कैन थिंक, सपोज देयर इज ए एब्रेशन, you, it is not necessarily that a process will be desired. Suppose you have made a product and that product is undergoing abrasion or wear due to its when we are using it. So when it is wearing, then that its value is getting reduced, like its surface finish is getting deteriorated day by day. Or you can say that it's suppose you have made a bearing, you know bearing, right? So gradually when it is with the passage of time, when you are using it repeatedly, so it will undergo wear and tear, and it's gradually a time will come that it will not fit into the into the gaps of the teeth exactly, or the a gear will not fit into the gaps of the teeth exactly, or a bearing won't exactly fit into the dimension it was exactly supposed to fit into, or the surface finish will gradually get deteriorated. So that is how its value is getting diminished, or the value is getting removed. So that is will be a value removal process. It did not necessarily be that you will intentionally do the process. It might just come on the basis of usage, but it will be a value removal process in that case.
Yes, sir. Got it.
So now is it clear what is value removal, value addition, and how it is totally different from a negative process?
Yes, sir.
Okay, so let me just write it. So value removal process, the final product will have lesser value slash you can write usefulness than the pre-processed counterpart. And what will be value addition? A process which essentially will add value or usefulness to a product. So in this value addition process, the value will increase in the final product. And essentially, let me just write it the for the negative process. So negative process will be a mass removal or subtraction process. That is what that you all were referring to, but that is a mass removal or mass subtraction process, not a value. So this the correct answer will be option number uh, D.
D.
D. It will be a value addition process. Okay, so I hope it is clear to everybody. If there is any doubt in any of these terms, you can just ask. Else we'll move on to the next problem.
सर
Yes.
सर वैल्यू एडिशन प्रोसेस में तो कुछ एडिशन हो रहा है ना.
एडिशन एज ए वैल्यू मतलब आप ये समझ सकते हो कि एज ए सपोज उसका अगर आप एक पहले प्रोडक्ट ए ले रहे हो और उसके बाद आप टर्निंग करके उसका सरफेस फिनिश बढ़ा रहे हो और डायमेंशन उसको एग्जैक्ट कर रहे हो तो उसका सपोज वैल्यू बढ़ गया. जैसे आप ऐसे मान लो कि उसका प्राइस बढ़ गया. एक फिनिश प्रोडक्ट का प्राइस हमेशा एक अनफिनिश प्रोडक्ट से ज़्यादा होता है ना. तो दैट इज हाउ ए वैल्यू इज बिंग वैल्यू उसको ऐड किया जा रहा है.
ओके सर.
तो अभी क्लियर है या एनी अदर डाउट?
यस सर.
ओके ओके. अगर फिर भी कोई डाउट हो तो यू कैन आस्क. ओके सो लेट मी मूव ऑन टू द नेक्स्ट प्रॉब्लम. So the next problem is related to this. So there are different processes by which we treat a material to improve. Suppose after a product is manufactured, we can then perform some other categories of operations such that its properties improve or some of its specific properties improve. These processes are also can be classified as value addition process. Okay. So like आपने we are making a cylinder. अभी the surface finish of that roller has to be improved. So we are doing some surface operations. we are polishing it, or grinding it, or polishing it, or lapping it, then we are adding value to it. And the more we do these processes, the more its value will be increased. And that is how this value addition process comes into comes into play. So the of these the processes that we do in after a object is manufactured, some may be used to change the bulk properties, and some may be used only to change the properties at the surface level. So the properties of this bulk material can be improved by which of these processes: a case hardening, surfacing, tempering, or coating. So any idea what will be the correct answer?
Case hardening.
Okay, case hardening. Any other answer?
Surfacing.
Okay, okay, surfacing. So, what is surfacing? Can you just give any just brief idea about what is surfacing? Anyone has any idea about what are these processes like case hardening? What is case hardening? What is surfacing? What is tempering? And what is coating?
सर सिर्फ कोटिंग पता है अच्छे से और थोड़ा सरफेसिंग.
Okay, so what is coating?
सर कोटिंग में जैसे गैल्वेनाइजेशन प्रोसेस होता है, जैसे कोई चीज़ है उसमें हम कोटिंग कर देते हैं, फॉर एग्जांपल लैपिंग, पॉलिशिंग, लाइक दैट.
Okay, तो उससे क्या होता है?
जैसे सर कोई मटेरियल है सपोज मेटल का, तो
अच्छा,
इट कंट्रोल्स फ्रॉम रस्ट.
ओके, तो कोटिंग हो गया। और सरफेसिंग के बारे में क्या पता है?
सर सरफेसिंग सर इज लाइक सरफेस फिनिशिंग.
ओके, सरफेस फिनिशिंग। ओके, तो इनमें से
I think the correct option is case hardening.
ओके, तो व्हाट इज केस
Because
हार्डनिंग?
increase the hardness of the outer surface of the
ओके,
material.
outer hardness of the material, and what is it seeking? It is seeking the properties of the bulk material. So what is bulk material, you know? What is called bulk material? Anybody has any idea? Okay, so what is bulk material? Bulk material is what is called bulk. It is a very common word, right? What is bulk? Anybody? Yes, anybody? What is
Sir,
bulk?
dry materials, bulk materials means.
Bulk material means?
Sir, some kind of dry powdered materials.
Okay, okay. No, actually that is not what bulk material means. So bulk material means bu- bulk material means a material overall. Like suppose you are taking overall the entire material under consideration. Okay, so supposedly we have taken this cube as a product. So bulk material of this cube will build the entire cube. Bulk is basically associated with the word volume. Okay, so the entire volume of this material, whatever material we are considering, the entire material will be considered as a bulk material. That is, whatever product we have manufactured, the entire thing is the bulk material. It is the bulk of material. Like when we consider the bulk material, it will consider the entire volume or mass. Okay, so when we are when we are talking about bulk material properties, we essentially mean that the property of the entire component, that is property of the entire component. So have you understood what is bulk property? So can you give an example on this kind basic definition of bulk material property? Can any one of you give any example of a bulk material property?
Sir, stone.
No, that is an that is not a, yeah, stone will be. I'm asking about the property. Like what will be the property of the stone that we can tell that this is a bulk material property? Like properties, I mean like density, temperature, pressure, all those things. So what will be a bulk material property? Bulk material, stone is a bulk material. But which properties of the stone can be classified as bulk material properties? Any idea?
Sir, maybe its entire mass.
Yes, exactly. What
Sir,
else?
shear stress elasticity,
Shear stress and
elasticity.
okay. Why shear stress and elasticity? Well, shear stress is not essentially as a property of any material as a whole. You can say that the shear limit or the shear strength of the material. So
Okay.
shear stress is no property. Shear strength can be a property. Other properties like thermal conductivity, electrical conductivity. You know about these properties.
Yes, sir.
So
Yes, sir.
are these something like they will be if you take a particular stone, like it is a, we are considering a homogeneous object here, there is a simple pure material something, or pure alloy with homogeneous distribution. In that case, will it be something that the electrical conductivity at the top will be something different, totally something different than the center, or it will be overall it will be having a uniform electrical conductivity?
Sir, if it is a pure metal,
Mm.
then the thermal conductivity will be higher.
Not higher or lower, I'm saying will there be any difference in the property value from its center to the surface if it is a homogeneous, like if it is uniformly distributed? Well, so what I am trying to say is that these bulk material properties are the properties of the entire system, or if, when we are considering this uh, cube as the system, then this entire cube, whatever property of the entire cube is there, like whatever is the electrical conductivity of the cube, or whatever is the thermal conductivity, or whatever is the magnetic property of the cube, or whatever is the optical properties of the cube, those can be classified as a bulk material properties. But the hardness, or you can say surface roughness. So these are on a particular surface, or hardness you can measure at the top surface or at the bottom surface, or surface roughness also you can measure at the top surface or the bottom surface. So these are the surface properties, and bulk material properties are basically the volumetric properties. So to have a easy differentiation, you can consider whatever uh, properties we specify as a surface are the surface properties, and whatever properties we use volume for their specification are the bulk material properties. Okay, somebody has a question, you can ask, please go ahead. Love Kush Kumar, you have raised a hand. If there is any, if you have any question, you can please ask. Okay, so yeah, please.
सर बल्क मटेरियल, ये बल्क मटेरियल के बारे में जानना है, ये किस तरह का होता है?
आपका वॉइस अच्छे से नहीं आ रहा है, पीछे कुछ साउंड आ रहा है, तो आप थोड़ा क्लियरली बता पाएंगे?
हाँ सर, बल्क मटेरियल में क्या क्या प्रॉपर्टीज होती है जानना है।
अच्छा, बल्क मटेरियल में जैसे कि आप इलेक्ट्रिकल कंडक्टिविटी ले लो, आप थर्मल कंडक्टिविटी ले लो, आप थर्मल डिफ्यूजिविटी ले लो, आप यहाँ तक कि अगर यूनिफॉर्म होमोजेनस एक मैटर है तो आप डेंसिटी ले लो, ठीक है। तो ये सब प्रॉपर्टीज जो पूरे आप एक तरफ से समझ लो, जो पूरे वॉल्यूम में सिमिलर होगा वैल्यू, ठीक है। आप अगर अभी डेंसिटी लेते हो तो उसका वैल्यू अलग अलग जगह पे अलग अलग होगा क्या इस सॉलिड में, अगर होमोजेनस सॉलिड है तो?
सर सेम होगा इफ इट इज होमोजेनियस।
हाँ
Yes, sir. It density is all over same.
हाँ, तो हम डेंसिटी को अभी हम लोग सरफेस प्रॉपर्टी बोलेंगे या बल्क मटेरियल प्रॉपर्टी बोलेंगे?
So
क्या सर
bulk.
सर रिपीट करना।
तो आप डेंसिटी को हम लोग अभी सरफेस प्रॉपर्टी बोलेंगे या बल्क मटेरियल प्रॉपर्टी बोलेंगे?
सर अभी तो बल्क मटेरियल प्रॉपर्टी बोलेंगे ना।
हाँ
bulk material property.
हाँ, बल्क मटेरियल प्रॉपर्टी। ओके, सो अभी आप इसमें आपको इन प्रोसेसेस में ये जो कोटिंग प्रोसेस है वो सरफेस प्रॉपर्टी को इम्प्रूव कर सकता है या बल्क प्रॉपर्टी को इम्प्रूव कर सकता है? आपको क्या लगता है इसमें?
Sir, surface को.
ओके,
Surface property, sir.
तो आप लोगों को ये which all of these processes do you know, like case hardening, do you have any idea, or then I will go through what is case hardening.
सर ये बल्क मटेरियल कलर कोटिंग वगैरह में आता है क्या?
नो, बल्क मटेरियल प्रॉपर्टी में कलर
किसी
कोटिंग
किसी
वगैरह,
चीज पर कोटिंग करना?
कोटिंग आप सरफेस पे करते हो या उसके
सर
इंटीरियर पे
हाँ
करते हो?
सर फिक्स है।
हाँ, तो वो सरफेस प्रॉपर्टी हो गया। जब तक आप अभी आप समझ लो एक
जी
एल्यूमिनियम का ब्लॉक है और एक आयरन का ब्लॉक है, ठीक है।
जी सर।
तो एल्यूमिनियम का डेंसिटी एक पर्टिकुलर वैल्यू है और आयरन का एक पर्टिकुलर वैल्यू है डेंसिटी का,
ठीक सर।
ठीक है। तो अभी आप अगर उसके सरफेस पे आयरन के सरफेस पे कुछ लगा दो या एल्यूमिनियम के सरफेस पे कुछ लगा दो, तो उसका डेंसिटी चेंज होगा क्या अंदर के मटेरियल का?
नहीं होगा सर।
तो वो डेंसिटी हो गया बल्क मटेरियल प्रॉपर्टी।
बल्क
लेकिन
मटेरियल।
वो जो आपने ऊपर जो लगाया उससे आपका सरफेस फिनिश या आपका ऑक्सीडेशन रेजिस्टेंस या आपका कोरोशन या रस्ट लगना, जंग लगना, ये सब रुक सकता है। तो वो हो गया सरफेस प्रॉपर्टी, जो वो सब इंप्रूव कर रहा है। जैसे कि सरफेस फिनिश इज ए सरफेस प्रॉपर्टी। आपका सरफेस कितना उबड़ खाबड़ है, हाउ मच रफ इट इज, दैट इज क्लासिफाइड एज ए सरफेस प्रॉपर्टी। वो सरफेस कितना हार्ड है, कितना सॉफ्ट है, ठीक है, तो वो कितना हार्ड है, कितना सॉफ्ट है, ये भी एक सरफेस प्रॉपर्टी है। अभी एक मेटल का ब्लॉक और एक स्पॉन्ज के ब्लॉक का, दोनों का तो हार्डनेस सेम नहीं रहेगा ना। सपोज एक रबर का ब्लॉक है और एक मेटल का ब्लॉक है, तो दोनों में हार्डनेस किसका ज्यादा होगा?
मेटल का ज़्यादा होगा।
हाँ, तो मेटल का हार्डनेस जो है वो तो आप सरफेस पे ही देखते हो ना कि उसका हार्डनेस क्या है।
जी सर।
तो
तो उस
उसमें,
पर जो कोटिंग होगी उसको बल्ब मटेरियल,
हाँ
उस
तो
पर जो कोटिंग होगी उसे वो बल्ब मटेरियल बोलते हैं।
नहीं नहीं, कोटिंग को हम लोग, कोटिंग करके आप सपोज आप रबड़ पे एक आयरन का कोटिंग चढ़ा दो, तो उससे क्या इंप्रूव होगा? डेंसिटी इंप्रूव होगा या सरफेस रफनेस इंप्रूव होगा?
सरफेक्स होगा।
हाँ, तो कोटिंग जब आप रबड़ पे एक आयरन का कोटिंग चढ़ाए, तो उससे जब सरफेस, सो व्हेन दिस सरफेस कोटिंग से जब अगर आपका सरफेस प्रॉपर्टीज इंप्रूव हो रहा है, तो बेसिकली कोटिंग से आपका बल्क मटेरियल प्रॉपर्टी, आपका कोटिंग चढ़ाने से, क्योंकि डेंसिटी में कोई चेंज नहीं हो रहा है, देन हाउ विल इट, कोटिंग कोई बल्क मटेरियल प्रॉपर्टी को इन्फ्लुएंस नहीं कर पाता है। So supposedly आप okay, let me continue in English. So whenever, suppose there is an aluminium, suppose there is an iron block and we are making a coating of aluminium over it. Okay, so
ओके सर।
on an iron
I
block.
think, sir, case hardening is the option and tempering also, I think.
Okay, so just wait. Let me just clear the coating, the bulk material and surface property with Mr. Love Kush Kumar, and then I will go back to it. So when we are making a coating of aluminium on iron, so with
जी
because of
सर।
that coating is the surface, suppose the rusting resistance of iron is prevented, or the density of iron is changing? Which one is happening?
ओके।
So you understand that due to coating, the surface properties can be changed, but the density and such other volumetric properties cannot be changed, right?
सर ये बल्क मटेरियल अपने हार्डनेस वगैरह भी बढ़ाता है।
Bulk material में हार्डनेस नहीं आता है। Bulk material will consider properties like density, electrical conductivity, thermal
डेंस।
conductivity, like that. Hardness is a surface property. आप कोटिंग करके सरफेस के हार्डनेस को बढ़ा सकते हो, तो वो सरफेस प्रॉपर्टी है, वो बल्क मटेरियल प्रॉपर्टी नहीं है। सो हार्डनेस इज ए सरफेस प्रॉपर्टी, नॉट ए बल्क मटेरियल प्रॉपर्टी। Like when we do hardness is also a property of the entire component, but when we do a coating, only the hardness of the surface layer, up when you do the coating, hardness of only the top layer or top layer of the component will change. Okay, so coating, when you are doing a coating, the hardness of the something like at the center, hardness of the center will not change. Then coating is not changing the bulk material property, it is changing the surface property, whatever be it, hardness or surface roughness or whatever it is. Is it clear?
Sir, I think also tempering is correct answer.
No, is the difference between surface surface property and bulk material property, is it clear to everybody?
Yes, sir.
Okay, so
Yes, sir.
Lavkush Kumar, if your answer is like if your question is answered, you can lower your hand. Uh,
ओके सर।
okay. So going to the processes, so what is case hardening? In case hardening,
जी
uh, basically it is used for low to medium carbon steels, uh, in which after the after a component is made, we are infusing carbon or nitrogen or any combination of carbonitrile compounds, so that these carbon, they diffuse to the surface layers, and these carbon infusion into the surface layers will make them harder. I hope that you all know that a low carbon steel is softer and a high carbon steel is harder. So for a basic low carbon steel like mild steel, okay, we want the surface to be harder. What will we do? We will infuse carbon into the surface, just into the surface, so that the surface becomes harder, and the entire bulk remains softer, only the surface is hardening. So that is called case hardening. Okay, so I hope the concept of case hardening is clear.
Yes, sir.
Okay, so now coming to uh, surfacing. What is surfacing? Surfacing refers to all the processes.
Sir, can you show the previous slide?
Yeah, okay.
Okay, sir.
Okay, so surfacing refers to all the operations done to improve the surface properties, such as surface roughness. Okay, like if you are polishing a component, then it is a surfacing operation. Okay, then coming to ostempering. So ostempering is a process of heat treatment. It is a heat treatment process. Do you know what is a heat treatment process?
Yes.
Yes,
What happens in a heat treatment process?
sir. Heat about the recrystallization. No. Yes, sir.
Uh, that is the recrystallization temperature thing. Yeah, it is partly correct. But what happens if there are different values of temperatures where the grains can change their shapes? Like, have you seen the iron carbide diagram?
Yes,
Yes,
sir.
sir.
So you can see that there are different mm, phases.
Structures of BCC FFC
Yes, sir.
structures.
Yes, austenite, ferrite, Fe3C, alpha Fe3C. So there are different phases. So basically, what is a heat treatment process? Heat treatment process will basically do what? It will heat a component to a particular temperature based on what end product we need, and then it will uh, do a cooling process. And this cooling process, depending on this cooling process as well, the final product will be produced depending on at the rate at which it is cooled. So it is a heat treatment process in which, so basically from the steels that we use, basically the medium carbon steels, what happens in those is that they have either a high hardness or a high ductility. Okay, so to improve these properties, what we heat these components and then we cool them such that a structure, called, in which is microstructure called bainite. If you have gone through the iron carbide diagram, you will see bainite on the right hand side below the pearlite regions. So this bainite structure is formed. So what happens is that due to the formation of bainite, the ductility at high hardness is achieved. Okay, so this is an improvement of the properties of the entire component. Like the entire component will be heated, the entire component, the phase will transform to this bainite, and the entire properties of the entire component will be changed. Okay, and coming to coating, in which a layer is applied on the surface of a component to improve surface properties. Like corrosion resistance. Just as somebody said, galvanization. So galvanizing the iron, it is basically a coating of zinc and its alloy given on iron such that the corrosion resistance increases. So only the surface is being prevented from corrosion. The any iron rod, the surface by galvanization, by coating, the surface can be prevented from corrosion, but at the center none of its properties is being changed. Okay, so is it clear to everybody the processes? Now based on these processes, if it is clear, tell me which one will be the, changing the bulk property.
Sir.
Yeah, can you please repeat?
Yes, sir. Tempering process is the right answer.
Os tempering, it is not tempering, it is os tempering.
Yes, sir. Os tempering.
Okay, so is it clear to everybody?
Yes, sir.
Okay, uh, mm, so somebody is asking to repeat the first question, but is there any particular specific doubt associated with the first question? Hello, is whoever was asking me to repeat the first question, was there any specific doubt related to the first question? Okay, you can just unmute yourself and you can just ask. Chaitali Patil, you can just unmute yourself and ask. You can't understand the question. Okay, so mm, basically a mild steel rod, okay, a mild steel rod, it was initially having 50 mm diameter. Now it has been turned. Turning is an operation in which we reduce the diameter of the of whatever object we are considering. So we are reducing its diameter to 40 mm, and it is a finished product. Okay, so this finished product, it is having a higher usage, like its value is higher than this initial product of 50 mm. How? Suppose this rod is to be fitted into a hole which has a diameter of 41 mm. So this 50 mm diameter rod cannot be fitted into that 41 mm diameter hole. So this 40 mm diameter object can be easily fitted into a hole of diameter, suppose 40 or 41 mm. So its value, its usage as a product is increasing. That is why it is a value addition process. I hope it is clear now. Okay. Okay. So we will move on to the next problem. Okay. So a plastic deformation in metal forming can be realized only when the applied stress is higher than the ultimate stress. Applied stress is below the yield stress. Uh, uh, Sorry, there is some typo, I guess.
Sir, Ostempering was the correct answer of second one, na?
Yes, Oz tempering was the correct answer. Okay. So the plastic deformation in metal is possible only when the applied stress is higher than the yield stress, applied stress is below the yield stress, applied stress is higher than the ultimate stress, and or the yield strength is lower than the ultimate strength. So any idea about this? Any idea about what is yield strength, what is ultimate strength?
Yes, sir.
Yes,
Yes, sir.
sir. Yes, sir.
Yes, sir.
So what will be the correct answer?
Sir, higher than the yield stress, the
Okay.
plastic deformation occur.
Okay. Yeah, correct. So if we see the stress strain curve of a general stress strain curve we are taking of a deformable material. In that case, this is the yield strength. This is the yield strength of the material. Okay, below this, if there is a, if we apply any stress below this, when we uh, withdraw the stress, then the mm, material or the component will revert back to its original shape. That is, this is the elastic limit. Okay, below this limit, if there is any stress given, then the whatever deformation it had till then, till this point, it will be reverted back to zero or nearly zero when the mm, stress is withdrawn. After the yield strength, if we apply a stress beyond the yield strength of the material, it will not revert back to its original shape. That is the yield strength. And what is the ultimate tensile strength?
The material will be deformed.
Yes, sir. Anuj is correct.
Material will be deformed.
Means plastic deformation will be started. मतलब
Dead.
yield strength के बाद plastic deformation start हो जाता है, but UTS will be the maximum
Maximum.
strength.
So what happens after UTS?
So fracture
It
point is
completely
occurring.
deformed.
Yeah, so ultimate tensile strength is the point after which the material fractures. So from yield strength to ultimate tensile strength, it is the plastic deformation zone. So to have this plastic deformation in the metals, we have to apply a stress that is beyond this yield strength. Okay, so the correct option will be option number C. So I hope it is clear to everybody. If there is any doubt, you can ask.
Clear, sir.
Okay.
Clear, sir.
Okay, so let us move on to the next problem. Is in case of the rolling process, the metal stock is passed through a die and forged by a plunger, squeezed through a closed die forging, two rolls rolling in the opposite direction or two rolls rolling in the same direction. So what will be the correct answer? You have an idea about the rolling process?
Yes, sir. Sir,
Yes,
two
sir.
rolling in opposite direction.
Okay, so what is the first one? Die and forged by a plunger.
It is the process of die casting process.
Is it essentially a die casting process? Only die casting process. What other
No,
forming
no, sir.
processes?
Yes.
You know extrusion process.
Yes, sir.
So
Yes,
what?
sir.
So what happens in an
Yes.
extrusion process?
So it is uses for thin wire.
No, no, no. How is the process done? What is an extrusion process? So basically, in an extrusion process, you have something like this.
Sir, wire pulling process.
So wire pulling process. Wire pulling process is extrusion process. Do you understand this process? What is shown here?
Yes, sir.
So what is happening in this?
सर कोई
This is
मटेरियल है.
forging process.
Yes. So this is an extrusion process. What happens is that this is this die with a desired shape of the hole from which you want to
Yes, sir.
process the material.
Orifice. Orifice.
Yes, orifice. So there is the metal is on one side of it and the plunger. This is the plunger, and it is forcing this material to move out. So the process one, the process A, it is essentially a extrusion process or not? I hope it is clear how the process A is an extrusion process.
Yes, sir.
Okay. So, and what is the process B? Squeeze to a closed die forging. You know what is closed die forging operation?
Can you repeat, sir?
What is a closed die forging? What is a closed die forging?
No idea.
Okay, so, you know open die forging or closed die forging, you have no idea, right? So, supposedly there are two dies. Okay, these are two die, and there is a material within this. This is the metal that we are trying to form. So, these two dies, they are open. There is no limitation in the movement of this material in these two direction. Is there any restriction to the movement of this material? Yes, exactly. So this is die, open die forging. Okay, so it is not enclosing the material, and there is no restriction to the movement of this material in these two directions. But in closed die forging, what will happen? Suppose we are taking dies of this shape, and this is the material that we are forming into this shape. So there is a restriction, it is enclosed, these dies are enclosing this material from all sides, nearly all sides, and there is a restriction to the final there is a restriction of the final shape, that is there is a restriction of this material to flow in this direction or this direction or this direction. It cannot flow because it is enclosed. So this is a closed die forging operation. Okay, I hope it is clear. And what is a rolling operation? So in rolling operation there are two rolls. It moves in this direction, the stock material, this is the stock material, and it comes out from this direction. Okay. So this basically it is with this, if we keep the width constant, then the length will be increased as the thickness reduces. So these rolls, what will be the direction of rotation of these two rolls? Clockwise, anti-clockwise. What will be the direction of this top roll?
सर टॉप रोल का
Yes.
Clockwise.
Anti-clockwise.
Okay. Clockwise or anti-clockwise? Anybody who is saying clockwise? Clockwise. Okay, so Chaitali has said that it will be clockwise. So if it is clockwise, okay, and what will be the direction of the bottom roll?
एंटी क्लॉकवाइज
Okay,
बोथ
anti-clockwise.
विल बी इन अपोजिट डायरेक्शन
Okay, so essentially, so what will be the direction of force in this direction? This will be the direction of force. And for the top roll, this will be the direction of force. So if we are feeding the material in the stock from this direction, how will it come out from this direction if the force is in this direction? If you are feeding the material from the right, from the left to move to the right, and the rolls are giving force in the left, this is the left force, then how will the roll come out from the right hand side in this case?
सर टॉप रोल विल बी इन एंटी क्लॉकवाइज एंड
Yes,
सेकंड वन इज क्लॉकवाइज
yes. So have you understood why this is clockwise and anti-clockwise?
यस सर
Any doubt? Anybody has any doubt regarding this? Anybody has any doubt about the direction of the rolls?
No, sir.
Yes, hello. No doubt, right? It is clear, right? Okay. So the correct answer will be option number C. Okay. I hope it is clear to everybody.
सर एक बार क्वेश्चन नंबर 4 वाली स्लाइड दिखा देना
If you are trying to keep this as a backup, like if you are trying to note this down, I would like to tell you that you will be given access to these videos in by the NPTEL team, so you can just understand.
यस सर
Okay, so let us move on to the next problem. Entrapment of atmospheric gases inside the casting may lead to which of these? Defective casting, residual stresses, dimensional inaccuracy, or pores in casting? What will be the correct answer?
Sir, maybe dimensional inaccuracy or pores in casting, maybe.
Okay. So what do you know what is entrapment of atmospheric gases?
ये सर जब कास्टिंग प्रोसेस होते वक्त जो उसमें गैसेस चली जाती हैं वो वॉइड्स क्रिएट करती हैं उसको एंटरटेनमेंट बोलते हैं.
Huh. So and तो
I
ये
think option D is correct.
okay, option D is correct. Yeah, option D is correct. It results in pores in casting because when the gases are going inside a casting, it will create voids. So, are these voids so large that it will result in dimensional inaccuracy? Or what is the primary reason for dimensional inaccuracy? What is the primary reason, or what are the most important reasons for dimensional inaccuracy in casting?
सर
Bigger the
डायमेंशनल.
cavity or pattern uneven.
Sorry, can you please repeat?
Battery is fully charged.
Cavities may be larger than these things, or the pattern is not proper.
Okay, yeah, pattern not being proper is one of the cases. But that is just a setting, like that is how that we can consider as a defect, or that can be a problem of the experimental set sorry, manufacturing setup. Other than that, what properties may or what phenomenon during the casting process may result in dimensional inaccuracy?
Shrinkage, shrinkage,
Shrinkage,
shrinkage,
yes,
shrinkage,
yes, exactly, shrinkage. So
shrinkage.
shrinkage, if we do not actually take care of the shrinkage allowance completely, then the dimensional inaccuracy is one of the foremost problems that are coming with the casting. Another thing that can result in a dimensional inaccuracy is the thermal expansion coefficient. So I hope the thermal expansion coefficient is clear to everybody. Do you know what is thermal expansion coefficient?
Yes, sir.
Yes. So how does the thermal expansion coefficient leads to the dimensional inaccuracy? Any idea?
सर थर्मल एक्सपेंशन कोफिशिएंट मींस जैसे जब जो टेम्परेचर होता है उसका जब कास्टिंग होती है तो इट मे बी चेंज फ्रॉम वन स्टेट टू अनदर स्टेट. जैसे लिक्विड है वो धीरे धीरे सॉलिडिफाई होगा अप टू द एटमॉस्फेरिक प्रेशर, सॉरी एटमॉस्फेरिक टेम्परेचर. सो if maybe there will be entrap of the atmospheric gases, then it would be inaccuracy in the dimensions.
Okay. But I am saying uh, the thermal expansion coefficient from solid to liquid is different. That is actually being taken care of in the allowance. What other things are not taken care of is uh, even when like we are making a cavity, right? The cavity has to take care of the metal that of the molten metal which is poured into the cavity. After that, it will also happen that during the liquid, when it is the temperature is decreasing, it will have different thermal expansion. Even in the solid, when like it is cooling to the room temperature, there will be a thermal contraction. Okay, so if the riser, which is actually designed to take care of these mm, uh, shrinkages and contractions, if it is not properly designed, then that will result in a dimensional inaccuracy of the component. Other major thing is that when we are making the suppose in sand casting, we are ramming the sand. Then if the sand is not rammed properly, if the sand is not particularly, it is you know about the green strength, the dry strength. So if the particular properties of the sand are not met, then the sand themselves will also uh, they will bulge out, the cavity will bulge out at some point, or there will be dropping of sand into the cavity from some point. So all of these results in the formation in dimensional inaccuracies. Okay, so it is a very wide range of phenomenon, but is entrapment of gases a significant one in causing dimensional inaccuracy? So like if we are making a casting of aluminium or iron, can the entrapment of oxygen be so much that it will result in dimensional inaccuracy? So it is not that much. Okay, so the atmospheric gases, they occupy very small voids and results in porosity or porous castings, but they will not be significant enough to change the dimensions of the component. Okay, and any idea about what is this residual stress? So when we are heating this, when we are pouring the molten metal, it is at a such high temperature, maybe close to 2000 Kelvin, and it is coming down to the room temperature. So this high variation in temperature, there will be contraction and expansion at different places. So what happens is that there will be regions where supposedly the material has contracted in such a way that it has given a tension on the it has resulted in a tensile stress in the component. Okay, suppose this is the component that we are manufacturing, and as it cools down from melting point to room temperature, there will be contractions, and these contractions may not be uniform. Okay, due to different reasons, maybe alloying, maybe due to this entrapment of gases, maybe different reasons, or due to this difference in the thermal expansion coefficient, which is a significant phenomenon, significant factor that is affecting this residual stress. So there will be contractions resulting in residual tensile stresses. Residual stresses, in general, we are referring to tensile stresses. Suppose if they are contracted in such a way, these two directions, they contract in such a way that there is a tensile stress developing in this direction. Okay, so what happens in this residual stress? So as a tensile stress is already in by default, it is coming into the component. So at whatever ultimate tensile strength or yield strength it was supposed to undergo deformation or undergo fracture, it will now undergo at a lower value of tensile stress. So that is a negative effect of tensile residual stress. So is it clear how this is coming?
Yes,
Yes,
sir.
sir.
Okay, and so the gases, the entrapment of gases will only result in the porous castings. Pores in casting. Okay, so I hope it is clear. We can then move to the next question, which is very basic one actually. So the property of material to transfer heat at a faster pace is which one? Which one of these?
Thermal conductivity.
B. Thermal conductivity.
Okay, so
Yes,
what?
sir. Thermal conductivity.
Okay, so the answer is D, thermal conductivity. So just to clarify, what is thermal emissivity? What is thermal emissivity?
So it is denoted by K, and
That is thermal conductivity is denoted by K. I am asking what is thermal emissivity, the option A.
no idea.
Okay, so just a minute. Hmm. Okay, so thermal emissivity is the it is the ability of a material to radiate heat. You know radiation heat, right? So if a material is heated, it will radiate heat. So thermal emissivity is the ability of a material to radiate heat with respect to a black body. Okay. Okay. Infrared energy. So heat, yeah. If we consider mm, infrared as the only sole form of heat energy, which is basically heat energy, the ability to radiate heat. Okay, you have written the measure of an object's ability to emit infrared energy. So the emission, like this emission occurs. I hope you understand that this emission occurs irrespective of the medium it is in contact with. Then thermal reflectivity. It is similarly the ability to reflect heat. Electrical conductivity is conduction of electricity, and thermal conductivity is the ability to transfer heat. Okay, so thermal conductivity, it is associated basically with conduction heat transfer. I hope you understand that there are three modes of heat transfer: conduction, convection, and radiation. So thermal conductivity is associated with the conductive heat transfer. Okay, so the answer will be option D, that is mm, thermal conductivity. It is denoted as K. It is the ability to conduct heat. Okay. Now coming to the next question. The metal is easy to cast if it possesses which of these? High melting point temperature, low solidification temperature range, low melting point temperature and low solidification temperature range, high melting point temperature and high solidification temperature range, and low melting point temperature and low solidification temperature range. I think so there is an error here as well. Yes, will be high. Okay, yeah. So we any idea about how to think about this problem? There are two factors. One is the melting point and one is the solidification temperature range. So how does the melting point affect? Which metal will be easier to cast?
So cast iron, aluminium, silver. This is easy to cast,
I'm
easy to
asking
melt.
on the basis of melting point, which metal will be easy to cast? Like higher melting point or lower melting point?
Lower melting
Lower
point.
melting point.
Okay, why so lower melting point? Why lower melting point?
So
जितना
giving a
लोअर मेल्टिंग पॉइंट होगा उतना ही इजी कास्ट करना होगा.
क्या?
जितना टेम्परेचर लोअर होगा उतना ही इजी कास्ट करना होगा.
Q. What is the reason? Okay, I'm writing that low melting point metals are easier to cast. But why?
So it's require less heat consumption, or we can say that,
Yes,
or
exactly.
and high solidification. It help to uh, pour at the maximum time.
Sorry, about solidification temperature range. High solidification temperature range will be what? How will it be beneficial?
High means it's going to pour the molten metal as as time as we can, because the solidification rate is very slow, no?
It is. I hope you are understanding what is the solidification temperature range. So, what is the solidification temperature range? Can you tell me? What is the solidification temperature range?
Sir, for non-ferrous it is 800,
I'm
and
asking what
ferrous
is
it's
for
about 12.
any general material. What is the definition? What is the physical meaning of this solidification temperature range? That is, do you have any idea about this?
The time going to take for the solidify the material.
Okay, okay. So
Huh.
I think that you were confused between solidification time and the solidification temperature range. So those two are different
Yeah,
actually.
at that particular temperature is going to be a mercy in a mercy zone, or we can say that in a solidification is going to be start over there.
Okay, so you were saying that it is a temperature at which the solidification will start.
Yeah.
But it is written as a range. So what is this range meaning?
Low to or in between two defined points.
What two
The
defined
range is
points? How do we define those 2 points?
say while solidification. So suddenly temperature goes down, and at the particular this things this time it's a constant for the particular time, and then again it's going to solidify. That we can say that Z type of curve. Oh no, sorry, yeah, like that.
Okay, I think that you might be confused in this. Okay, let me explain, and I hope that I'll just try to understand if it is clear or not. So just a minute. Okay, so what is solidification temperature range? Temperature range. Have you seen the solidification curve, or mm, yeah, the phase diagram of a alloy?
Yes, sir.
So can you tell me what happens in that? On the basis of that, do you know what is this?
Sir, it shows the transition from liquid to solid.
So this is the liquid plus solid region, and this is solid region, right? So this diagram, you know, right?
Yes, sir.
So at any particular composition, when we are decreasing the temperature like this, okay, at any particular composition, when we are decreasing the temperature like this, what will happen at these 2 points? This is the point where the solidification will start. That is, from the liquid region, phases, some certain regions of solid phases will start forming. This, at any point within this, it will be a mixture of liquid and the solid. And after this point, there will be no further solid, no further liquid, it will only be solid. So this range of temperature is called the solidification temperature range. So is it clear to everybody? Like, and it will be a function of the composition. At any particular composition, it will be a fixed value. As we change the composition, it will be different. So is it clear? What is solidification temperature range?
Yes, sir.
Okay. So what happens if the solidification temperature range is high? So what will be the physical impact during the solidification process if the solidification temperature is high?
Sir, repeat the question.
So for a high solidification temperature range, what will be the effect during this during a casting process? What will be the effect of a high solidification temperature or a low solidification temperature range in a casting process? Any idea from this diagram? Can you say what is the possibility? Okay, so what happens is that a wider range of solidification temperature implies that at a particular location it has already solidified, and at some other particular location it is still liquid. Okay, it may result in something that, suppose in the direction of solidification, if some region it has already solidified and some other region uh, still remains in the liquid phase. Depending on this composition, it may be such that the liquid remains entrapped uh, by this solid. It might also happen that in the liquid region there is a particular solubility of one metal in the other when we are thinking of the composition. As it solidifies, the solid state has a uh, lesser solubility of the alloying element as compared to the liquid state. Okay, suppose we are taking a alloy of nickel and iron. Okay, so in the liquid stage, whatever fraction of nickel is soluble in iron in the mm, uh, or you can say nickel and chromium. So in nickel and chromium, whatever fraction of nickel is soluble in chromium in the liquid phase, it will be lesser in the solid phase. So what happens is that when this range is higher, the higher this range, the more so as this solidification progresses, what happens is that nickel, which is less soluble in the solid phase than in the liquid phase, it will get rejected to the liquid phase. Okay, suppose this is solid, this has solidified, and this is the liquid region. Now, the solubility of nickel is less in the solid than in the liquid. So, it is less soluble here. So, this alloying element will start moving to the liquid region. Okay, so the greater this gap, the more will be the difference in this that whatever fraction will be solid and whatever fraction will be liquid, and more will be this rejection. And as this alloying element gets rejected to the liquid, this the composition of this liquid, it was initially supposedly before any of this solidification process began, supposedly it was 30% nickel in 7 and the remaining 70% is chromium. So since this nickel is now getting rejected back to the liquid, what happens is that now this will gradually increase, like from 30% this liquid is now becoming 31%, 32%. So this liquid is now becoming enriched in the alloying element. So there will be a time, it will come, that at the center of the as we move towards the center supposedly, so in this casting, if the solidification begins from these two directions, um, then at the center what will happen, it will have a totally different, totally like in the at the center, at the sides, it will be uh, the initial composition like 30% nickel and 70% chromium. But at the center, due to this process, what will happen, it will be much more nickel than chromium, or much more the alloying element will start pouring. Basically this alloying element will start moving from the faces from which the solidification starts towards the center. So it will result in a heterogeneous structure. Okay, so now after I have explained this significance of the solidification temperature range, now can you say is a high solidification temperature range or a low solidification temperature range will be beneficial? Any doubt or anything in the concept, you can ask whatever you have not understood in this, the solidification process and the solidification temperature range, the effect of the solidification temperature range. If you have not understood, you can ask. Anybody can just unmute and ask.
Sir, so the correct answer is low melting point and high solidification temperature.
So, are you understanding this problem? Did you understand that the alloying elements are getting segregated and it results in a heterogeneous structure? This thing that is happening here.
Yes, sir.
So, why does this happen? If this was a single line, okay, if this L plus S region did not exist, would such a heterogeneous structure form? Like for a pure metal it solidifies at a fixed temperature. There is no liquid plus solid region. It 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 solidifies immediately at a fixed temperature. It is a isothermal solidification process. So if this was a single line for a pure metal, will this heterogeneous structure form?
No, sir, it will not form.
Okay. So, and is this heterogeneous structure beneficial or it is a problem to our cause?
It's not beneficial. It's cause a problem, sir, because
Okay.
of utilities mix.
Yes. So, so what is causing the problem? This existence of this liquid plus solid region?
Yes, sir. Because it takes a lots of time to get solidified.
Just not lot a time. Uh, the time depends on the cooling rate again. It is this difference in the solubility or transfer of this alloying elements from the solid to the liquid region is what is causing the problem. So the existence of the liquid plus solid region is causing this heterogeneous structure. Is it clear to everybody?
Yes, sir.
Okay, so when there was no liquid plus solid region, there is no heterogeneous structure and no problem. And when this liquid plus solid region is existing, there is a heterogeneous structure and there is a problem. So the larger this liquid plus solid region, what will be? The problem will be more or less?
It will be more so.
Yes. So because the heterogeneity will be more.
Yes, sir.
Okay, so a higher solidification temperature range means what? Higher solidification temperature means this liquid plus solid region will be broader or narrower.
Sir, will be broader.
Yes.
Yeah,
So a broader the larger this liquid plus solid region, the broader this liquid plus solid region, the more will be the problem or the less will be the problem.
more will be the problem.
More will be the problem.
Yes. So now can you understand that with high solidification temperature range, it will be a problematic or it will be a beneficial to our cause? Yeah. What is it?
It will not beneficial.
Yes.
Higher
So
solidification temperature.
yeah. So we need low solidification temperature range is beneficial. I hope it is clear.
Yes, sir.
Yes, sir.
So what will be the correct option?
B.
Yes, option will be B. Okay, so I hope
B.
it is clear to
Yes.
everybody. Then we'll move on to the next problem. If there is any doubt, you can ask.
Sir, seventh question answer is what, sir? Sir,
Sorry,
the option D is correct.
option B.
No, no, sir.
Which?
Eighth question. I'm talking about eighth question.
Okay, question 8. Okay, we have come to it now. Hmm.
Okay, sir.
So yeah, so machining metals, HE breaker is required in which of these? Brittle metals harder than tool metals, uh, ductile metals giving discontinuous chips, or ductile metals giving continuous chips. So you have answered option number D. So what happens in case
Yes,
of
sir.
brittle metals?
Sir, the discontinuous chip is formed.
Okay. And if the metal is harder than the tool?
Harder than the tool.
Yes.
So, sir, there is no machining.
Yes, exactly. And
Yes.
in what cases the ductile material can give discontinuous chips?
Sir, feed rate is 2 more.
Yes, and what kind of chips are discontinuous? You know what is the shape?
Sir, shape नहीं पता है.
So shape are basically discontinuous chips. Shapes are basically they curl into each other. They become curls.
Yes, sir.
Okay,
Okay,
so
sir.
they become curls and they didn't become discontinued. Okay, Chaitali
Yes,
has
sir.
raised a question. You can go ahead and ask. Your voice is not audible, Chaitali. Your voice is not audible. The sound is very less.
Hello.
Yes, hello.
Ductile metals giving discontinuous strips and ductile metal giving continuous strips. What is the difference between them?
Okay. Let me explain this. So I think the brittle and hardened tool are clear to everybody.
Yes.
So for ductile materials giving continuous chips, sorry, just a minute. Okay, ductile plus discontinuous. Okay, so this happens when the chips form like this. When you are cutting a workpiece and the chips form like this, ductile metals can give a form like this which curl onto themselves, and after a particular curl is formed they get discontinued, like they break off at that point and they form the curls again, like they will form a chip like this. So these are the ductile discontinuous chips, and ductile continuous chips are such they will form chips like this, they don't break. This is mostly because for this ductile material, if the due to this machining process, if the chip material is not work hardened enough or strain hardened enough, I hope you understand what is work hardening or strain hardening. So if work hardened or strain hardened enough, then they will form these continuous chips. In this case, in this particular case, chip breaker is required.
Yes, sir.
So, Chaitali, is it clear what is ductile plus discontinuous and ductile plus continuous? Okay. So, the correct option here will be option number D. Okay. So, the next problem, identify the correct option. Casting is a zero process, machining is a positive process. I hope I have already explained what is a zero process, what is a positive process, and what is a negative process. So, can just you all type your answers in the chat box. I hope
Sir, option D is the correct.
option.
नहीं, एक सेकंड. No, एक सेकंड ना, sir.
You can type in the chat box. I would request all of the students to please type in the chat box so that I can like this is very basic one which has already been explained. So just take it as an assignment and just I request all of you to just type the answers in the chat box.
B,
Sir,
B.
answer B is
Answer
correct.
is
B.
Okay, B. Ha, it is option B. Okay, so I hope it is clear to everybody. Okay. Then the next question. Choose the favorable material property for the forming process. Be careful about the forming process. So low yield strength and high work hardening capability. Low yield strength and low work hardening capability. High yield strength and high work hardening capability, and high yield strength and low work hardening capability. So there are two aspects. The previous one we considered the casting. Now we are coming to the forming process. So there are two aspects. One is two factors that we are considering. One is the yield strength and one is the work hardening capability. So start with a yield stress and tell me, will a low yield stress or a high yield stress be beneficial for farming? I think all of you know what is yield stress. So a lower yield stress or a, yes, go ahead please. Which one will be beneficial, a higher yield stress or a lower yield stress?
Sir, low is better.
Okay, why so?
Sir, as per the sir process forming.
Sorry, your voice was not clear. Can you please repeat?
Sir, as per the forming process, the low yield strength is better.
Why? I mean, why is this better in the forming process? Why?
Sir, because we need plasticity in forming
Because
process.
because yes, sir.
So basically, the lower the yield stress, it will start deforming at a lower value of stress. That is why lower yield stress is beneficial. Okay. And what is work hardening capability? Anybody has an idea about what is work hardening capability? What is work hardening? Work hardening or strain hardening, they are same things. So do you have any idea what is work hardening? Okay. So supposedly we yes.
Work hardening means increase the hardness of metal. Metal induced and deliberately or accidentally by hammering.
By
Hammering.
okay. Well, hammering is not a phenomenon basically. What happens is uh, it is yes, it is the increase in the hardening, like it is increase in the hardness, or not increase in the hardness. It is basically increase in the yield strength of the material. Is how it happens is that supposedly when you load a give a stress, this one, this stress you are giving, and when you unload it, okay, after giving this value of stress, it is having this deformation, and when you remove this load, it will undergo a partial it will partially revert back to its shape. Like this was the initial shape, this point 1, and it will revert to this point. It will not revert to its exactly the original shape. It would have reverted back to its original shape if it was unloaded at this point, till this point. If anything beyond that the stress is applied and we unload it, then it will come back to this point, say epsilon dash. Okay, so this value supposedly when due to stretching, this one of dimension L was stretched to sorry, was stressed to L1. Now after this is withdrawn, it will revert back partially, say to a length L dash, which will be less than L1. Okay, it will come to this point. Now what happens in the next? Now if we apply the load once again, okay, what is the yield point defined as? Yield point is the point from which the deformation can start. So since this point, since this specimen, now this is specimen 1 and this is specimen 2, so the specimen 2 now already has this deformation L dash, like it is already at this deformation. So when you give the stress again, it will start deforming from this point, is not it? It will start deforming from this point. Is it clear how it will start deforming from this point? Any doubt in this? That when we will reload, when we apply the stress once again, say sigma 1 is applied again, initially it was before this cycle was done, the yield stress was this sigma naught, say the material started deforming from this point, okay. So now when the material has once you load it to the stress sigma 1 and you remove the load, it will already have this much of deformation. This deformation is called plastic deformation. Plastic deformation as in it is permanent deformation. Suppose this length L, if it was loaded till sigma naught is the yield strength value, then it would have retained, it would have come back to its original length L. Now, but we don't do that. We elongate it to some sigma 1 stress, using some sigma 1 stress which is more than the yield strength, and then we remove that load sigma 1. So it will come back partially to a length L dash. Now its length was initially L, now its length will become L dash, which will be more than the length L. This is a plastic deformation or a permanent deformation, that it cannot revert back further to the point to the length L. It will always have this deformation L dash. So is it clear till now? Okay. So after this point, when the length has become L dash from L, we start again giving the load. Now initially the material deformed at sigma naught. Now at which load will the material start deforming? Will it be sigma naught or sigma 1? Will it be sigma naught or sigma 1? When we are starting their deformation in this direction, or we are deforming L from L dash, it will start deforming by the stress of sigma naught value or sigma 1 value.
Sigma naught value.
Okay, so you were saying that it will start deforming from sigma naught. Is it so? So the curve, it will start deforming in this direction proportionally, right? So it will not reach this sigma naught curve. It will not intersect that the curve at that point itself. It has already undergone the deformation due to this difference sigma 1 minus sigma naught. So how will it deform from sigma naught again?
Okay, sir.
So understood. So it will start deforming from sigma 1.
Okay, sir.
So for this material, for the material specimen 2, what is the effective yield strength now? Yield strength is the point, is the value of stress from which it starts deforming, right? So initially it was sigma naught, but now it has it starts deforming from sigma 1. So what is the effective yield strength here? So the effective yield strength will be sigma 1. That is basically, so if you keep on repeating these cycles, from sigma 1 you move to sigma 2 and so on, so the effective yield strength and hence the hardness will keep on increasing. That you will need now, from initially when you were deforming, you needed a value sigma naught to deform it. Now you will be needing sigma 1, then sigma 2, then sigma 3 and so on to deform it. So basically, due to this process, the substrate or the component is getting hardened. And since it is done by working on the component repeatedly, on cycles you are working, so this is called work hardening or strain hardening. Strain because this is the epsilon value, the strain, epsilon dash value strain, this is the plastic strain value, which actually results in the work hardening. Okay, so that is why it is also called strain hardening. And since we do repeated cycles of work on the component, and which is resulting in the hardening of this component, that is why it is called work hardening. So I hope it is clear what is work hardening now.
Yes, sir.
Okay, so moving on. Hmm. So basically, this was one curve. This, let's say this is curve 1, the red one, and the green one is a curve, this one. Okay, till the yield point it is same, from the yield point it is different. So which one will have a more work hardening capability?
Green curve.
Yes,
The
green.
green one is
Huh. So and as the work hardening capability increases, so you see, for the same deformation, supposedly we need this deformation is required. We need to elongate to this point. Now, so for which one will be the stress be more required for deforming to this point, to this level? Like for a okay. Like for this value of deformation, we are willing to have this value of deformation. Then what is in which one, the green one or the red one, will have higher value of stress required for the same deformation? That is same strain, which one will have a greater value of stress requirement? You have understood the question, right?
No, sir, I didn't get, sir.
So the epsilon denotes what? Epsilon is the deformation. You understand that, right?
Sir. Yes, sir.
So for the same deformation, this is a vertical line, right? That is, the deformation is same.
Hmm.
The green, the material having the green curve or the material having the red curve will require a higher value of stress for this value of deformation.
Yes. Yes, sir.
Which one will require? That is what I'm
Green
asking.
one.
Green one. Why? Because
so
there is
always green one क्योंकि it is higher.
so the green one will require a higher value of stress. So basically, for the same value of deformation, a material having larger work hardening capability will always require a higher value of stress for the deformation. So if we have to give more and more stress, so it is becoming a problem for us in the forming process, right? We have to give the force manually or using some particular machine. So the higher the work hardening capability, higher will be the so higher the work hardening capability, more will be the stress required for a particular deformation. So it is beneficial or non-beneficial? Higher work hardening capability is beneficial or non-beneficial in this respect?
So not beneficial.
Okay, yeah. So this is not beneficial. So the correct option will be, which one will be the correct option?
So B, low yield strength and low work hardening
Yes,
capability.
exactly. So the correct answer will be option number B. So I hope it is clear. Let me move on. There are two more questions. So let me just quickly go through those. So in hot forming process, the substrate is heated to above the melting point, above the recrystallization temperature, below crystallization temperature, or just above the ambient temperature.
Of the
So above the
recrystallization
recrystallization
temperature.
temperature.
Yes.
The option
So
B.
yeah. So I hope it is correct, clear to everybody.
Yes, sir.
Yeah. Okay. And what above recrystallization temperature? What is the like range with respect to the melting temperature? Like what fraction of the what fraction of the melting temperature is usually the recrystallization temperature?
Sir, above the recrystallization temperature means we can deform it by hammering.
No, I am asking what is the fraction, like suppose if the melting temperature is 2000 Kelvin, what will be the range of this recrystallization temperature or an average, like approximate value?
Sir, don't know the range.
So
So
it is
0.3 to 0.4 approx.
you can it is actually 0.4 to 0.5
Okay,
of the
sir.
melting
Okay,
point temperature, but in Kelvin.
okay.
Okay, so I hope it is clear. Let's move on to the next problem. How
Sir,
does
please, sir. Previous slides. Okay, done, sir. Done.
how does high solidification temperature affect casting of alloys? It results in porosity. We have already explained how solidification temperature.
Sir, yes,
So
sir. Sir, option D is correct. Heterogeneous.
there will be a typo. Uh, temperature, not temperature. It is temperature range. Yeah. So I hope it is clear because we have already explained it previously. So it will result
Yes,
in
sir.
Yes, sir.
Option D
heterogeneous
is correct.
structure. Now for casting metals, what will be the favorable condition? The thermal expansion coefficient and melting point should be low, or what should be the thermal expansion coefficient and what should be the melting point? The melting point should be low is fine, but what should be the thermal expansion coefficient?
Sir, hi.
Why high?
Sir, as per the sir weather conditions, uh,
So what is thermal expansion coefficient? You know,
yes, sir. Elongated.
any kind of expansion when the temperature increases, right?
Yes, sir.
So when the temperature is coming down, as it solidifies, if the thermal expansion coefficient is high, it will contract more. Is not it? If a if an object, if a material has a higher thermal expansion coefficient, then as the temperature is decreasing during the solidification process, then the contraction, the thermal contraction will also be more. Is not it? Any doubt in understanding this? You can just speak up. Anything, whatever is coming to your mind, you can speak up.
Sir, option A and D both are same. Maybe there will be wrong something.
Yeah. One should be high. So what will be the effect of this thermal expansion coefficient? We need it a high or low.
Sir, I think both needed to be low.
Yeah. So the person who say that it should be high, is it clear why it should not be high? Because if it is high, then it will contract more, and we have to give a greater amount of allowance for that to happen, or we have to again account for that in the riser or any other allowance that has to be taken care of. So the higher the thermal expansion coefficient, more will be the contraction, and we don't want the contraction to be that much. So we want the contraction to be as low as possible. So the thermal expansion coefficient should be as low as possible. I hope it is clear to everybody. Any doubt in this?
No, sir.
Okay. Should be low, and melting point should be low. Okay. So the option is option number A. Both the thermal expansion coefficient and the melting point should be low. And the last question for today, in forming, the strength is higher in which direction? Longitudinal direction or transverse direction? Any idea about this? So what is the longitudinal direction? So if we are rolling it and the material is moving in this direction, then this is the longitudinal direction. And this is the transverse direction. This one. So minute. So when we are doing any forming process, the grains will start getting aligned in this direction, longitudinal directions like this. Okay. So in which direction will be the strength will be more, in the longitudinal direction or the transverse direction? Any idea?
Sir, in this we are talking about the forging process.
Forging process, rolling process, in any kind of forming process.
Okay.
So which one will be if we try to pull in this longitudinal direction and if we try to pull in the transverse direction, which one will be having a higher strength? That's what I am asking. So basically the transverse direction will be lowered in strength because supposedly when we are pulling in this direction, in the strength is direction, so since the grains are aligned in this direction, so they will be easier. So if we want to undergo a fracture in this direction, it might so happen that the grains that the fracture is happening in between the grains also, or since the or you can consider that the effective area of the grain boundary, in this the effective area of grain boundaries are only this and this and this, but in this the effective areas of the grain boundaries are much larger. So with larger values of the area for grain boundary, the larger will be the chance of deformation and lower will be the strength. So the strength will be more in the longitudinal direction and lesser in the transverse direction. You can consider like a supposedly a bamboo stick. Okay, if you can pull it in the longitudinal direction, like along the length, if you are pulling it, this pen, if you are pulling in the longitudinal direction, it will be very difficult to break it, right? You have to tear it off. But if we in the transfer direction, if we pull if we
Bend it.
bend
Like
it,
bend it.
yeah, if we try bend it in this direction, then it will break easily. Why this comes into like role is because in the forming this directional movement of these grains, directional flow of these grains is possible. In casting it gets solidifies, it starts getting solidified and forming grains at random orientations. But in forming these grains, since they are getting deformed, you are hitting about the recrystallization temperature and then you are deforming, so they get deformed in a particular direction. That is it, the grain flow has a particular direction, and hence they get aligned in a very directional manner. That is why this longitudinal direction will have a much higher strength than the transfer direction. So
Option C is correct.
option C is correct and option B is also correct. It will be lower in the transfer direction also.
Yes, sir.
So the option will be higher in strength is higher in longitudinal and lower in transverse. Okay, so it will be options B and C. Okay, so I hope it is clear to everybody, and I hope that your doubts could be cleared. So I hope this will be helpful
Yes,
for
sir.
you in solving the assignments, and in the session for next week we will be continuing further. And I request all of you to please join the session so that
Sir,
we,
sir,
yes, yes,
sir, next class will be on next Tuesday, right?
yeah, next Tuesday it
Because
will
next Tuesday will be on 15th of August, so there will be holiday or maybe class.
no, actually next Tuesday is not 15th of August. I think next to next Tuesday it will be 15th of August. But holidays also, we will be taking classes, like this is mm, like a special class, right? So I hope you can join.
Okay, sir.
There will be no holiday on 15th August. There will be class. Okay, so and please tell your friends also to join, so that like it's better to have a healthier discussion with a larger number of participants. So okay, I hope to see all of you in the next class. Okay,
Thank you,
and
sir. Thank you very much.
yes,
Have a good day, sir.
yeah, thanks. Have a good day. A good day to all of you, and yeah, please join. The sessions will always be on Tuesday from 6 to 8. Any changes in timings will be pre-informed. Other than that, it will always be on Tuesday, 6 to 8. Thank you. Thank you for joining.
Thank you, sir.
Okay. Thanks. Thanks. You may leave.